Hello. In this lecture, we're going to be discussing hash functions. Hash functions are a general computer science concept, but in this lecture, we will be specifically focusing on a set of properties of hash functions that specifically relate to how they are implemented in blockchains and how they're utilized in blockchains. At the same time, we will be looking at a few applications that are derived from these properties, applications which are enabled by these properties. So to get the definition out of the way, a hash function is basically a mapping. It takes values from a certain set of input values and it maps them to a certain set of output values. So there are some properties that we would like to see within a hash function in the specific blockchain context that we're dealing with. So I'll get to that shortly. So the first thing that we'd like to see in a hash function is that we would like for it to be deterministic. By deterministic, I mean that the hash function will always operate in a predictable manner. That is to say, if you have a certain input value, no matter how many times you feed it through the hash function to get an output value, you'd always get the same output value. Similarly, if you are to use a different input value, you would always get that same different output value for the different input. This is important, and we will see later why. Secondly, we would like to be able to take a string of any size as an input, and the hash function should give us a value which has a fixed length output. This is important because often we will be dealing with messages which have variable lengths, and we would like our hash function to be able to deal with all of them at the same time so that they can give us outputs and the program still works, the system still works. We would also like the computations to be quick. This is because we are going to be doing a lot of hashing in the context of blockchains, and if the individual computation is slow, that would obviously weigh the whole process down, so we would want the computation process to be quick. We would also like hash functions to be collision free. As for what this exactly means, we will get into this shortly in the lecture, but for now, just as a general idea of what this might mean, we don't want different input values of the hash to give us the same output value, and this will have consequences that we'll see later. We would also like our hash function to exhibit an avalanche effect. What this essentially means, and again we'll see this shortly, is that small changes in the input should give us large changes in the output. We would also like our hash functions to also contain what we call hiding properties, and we would also like these hash functions to be amenable to puzzles. So we'll visit many of these properties at length now. So if you're confused now, we'll deal with it shortly. Let's go through the avalanche effect. So basically, what we want our hash function to look like is our hash function should be able to function in such a way that even if we make a small change in the input, the output should look very different. So here in this example, if you look at the example closely, in the second row here, we have a sentence that says the red fox jumps over the blue dog. And in the third row, we have a sentence that says the red fox jumps over, O-U-E-R instead of O-V-E-R. So one letter changes in the whole sentence, the blue dog. So these two sentences are basically the same except for one letter. And when we put it through a cryptographic hash function, we quickly see that the output that we get looks very, very, very different. Now, this is important because if it were not different, then if the input was correlated, if differences in the input could be easily understood by differences in the output, then you can often backtrack and you can figure out what the input might be based on how the output is changing. So we don't want that sort of predictability in our system, which is why the avalanche effect is important, and we want the input to be very, very vaguely, if not at all, correlated with the output. So we talked about the collision-free property earlier, but just to get a sense of what this looks like, so suppose we have two values x and y, and we put these values through a hash function. After putting these values through a hash function, say h, so we would get hx and hy, which would be the hashes of x and y respectively. We don't want a scenario where x and y are different, and yet h of x and h of y are the same, which is depicted in this bit of a hash table that we have going on here. So if you look, so for different values of x and y, you should never have the same value of their hashes, which will lead to conflicts. So realistically speaking, collisions are not completely, it's not feasible to guarantee that collisions won't ever happen. So we would just like for a situation where they are very, very unlikely, which is to say that we would like a situation where collisions are infeasible, if not impossible. And the reason why and one of the important reasons why it's not possible to guarantee this is because we are remember the property that we talked about earlier, which is that we want to take any string of any size and we want to get an output of a fixed length. If that is indeed the case, we have a situation here where, like, basically we're in a situation where our input is basically the space of all possible strings, and the output is a finite set of strings because we have already earmarked what the length of this, we have already defined what the length of this output should be. As a result, if we're taking such a big input space and we're compressing it to a small output space, we would have a situation where we would of course have conflicts because there would be because we have limited space to work with on the output end. Given this, we just need to make sure that it's very unlikely and very improbable that we would have two values which are different and yet give us the same output. So just just an introduction to what it looks like in a programming language context. So Python has a library called hashlib. So here, if you basically, I won't go through the details here, but just to motivate how, just to show you an example of hashing, a getHash function has been defined here, which basically takes in a string and outputs the hash. So if you say hello crypto world, it gives you this hash as a result. Then you say another string gives you a separate hash as a result, and another string and yet again a very different hash as a result. They're all the same length, but they look very, very different. So this leads us to one of the important uses of hashes, and as they're also used in the context of blockchain, which is that we basically want to find a way to compress messages in such a way that we can still use them later on. So suppose you have two messages, and in the case of suppose in the case of blockchain, you can think of it as transactions. Suppose you basically have two sentences, and instead of storing two large sentences, we can choose to store small, relatively small versions of those documents in the form of the hash of that document. So, for example, if you have two messages x and y, instead of storing x and y directly, store the hash of x and the hash of y. Later on, if you have a new message z and you want to see if x and z are the same, you can basically just compare the hash of x with the hash of z, and you've only just stored the hash of x. So basically, remembering the hash will save you some space. And also, if at a later point in time, this same document x, someone brings it to you, but it ends up being corrupted, you'd easily be able to tell because you already have a hash of the original document x versus the corrupted version of x. So if you were to compare the two hashes, the two would not go well together. Next, as discussed earlier, we would like the hash function to exhibit a hiding property. So by hiding property, the first thing that is obviously pretty intuitive here is if we have a value x giving us a hash hx, and given hx, we would like for it to be difficult for you to find out x. So how is the hiding property implemented? Basically, this won't make a whole lot of sense now, but given a few more minutes into this discussion, I hope this will make sense. So we want to make it difficult for us to find x. So what we do is we concatenate x with a string r, and this string r would be chosen from a very spread out distribution. Again, this will be explained shortly why we make these choices. And then instead of hashing x, we hash the concatenation of r, which was chosen from a very spread out distribution, meaning all possible values, there are lots of possible values, and that they're all fairly uniformly likely. So instead of hashing x, we would hash r and the concatenation of r with x, and we provide that to the public. The reason we do this is because if you just hashed x, and if x had limited possible values, so suppose in this context where you're throwing a die, if there are only 6 possible values that you can have, as you can see here, hash of 1, hash of 2, hash of 3, hash of 4, 5, and 6. Given this space where there is a finite number of values, if you have just the hash of that value, it's still very easy to understand what the original value was, because you could just iterate and hash through, because the hash function is computationally efficient, as we discussed earlier. You could just iterate through each of the possible values, and then for the one value for which the hash matches the hash that we already have, we could say that that is the value of this. So to prevent this, what we do is, instead of giving them the hash of x directly, we can give them the hash of x concatenated with r from a very spread out distribution. The next application for hash functions that we'll be looking at is best understood by an analogy. So suppose we have a message that we want to send, and we want to put this message in an envelope, and we want to distribute it to other people. But we don't want this message to be revealed right away. However, because we want the message to be revealed at a later time, we also want a way to ensure that the message that we originally sent hasn't been tampered with. So that later on, when we claim that this was the message I sent you, there should be a way to verify that that was indeed what was put in the envelope. So to do this, what we're going to do is we're going to take the help of a function called commit. So what this function commit is going to do is it's going to take the message that we want to send, and it's going to concatenate that message next to a randomly generated value called a key. So if we just look at this slide here, the commit message function, what it's going to do is it's going to return the hash of the concatenation of the randomly generated key and the message that we originally wanted to send. And after this, what we're going to do is we're going to return this hash along with the randomly generated key that we have. Now, once we've used the commit function, we will immediately publish that hash. Now, that hash is what we refer to as a signed message here. So we are referring to a concept called signing a message. And by signing a message, I simply mean concatenating that message with the key and then taking the hash of the message and returning that hash as the signed message. So this is the signed message that I have committed to. Later on, so other people can see the signed message, but from this signed message, there is no way to infer what the original message is. Later on, I will reveal the original message. And at the same time, I will also reveal a key, the key that was used for that hash mentioned earlier. What we need now is a way to verify that the message that I'm claiming was inside that signed message is the same message that I originally committed to. To do this, we'll simply take advantage of the verify function, and the verify function will do the same thing. So what the verify function will do is that it will take the key that I've now published along with the original message that I claim was the message that I claim was the original message, and it will take the hash of that. If the hash of the key and the message is the same as the signed message that I revealed much earlier, then I am speaking the truth, and therefore the commitment has been maintained. So the value of the message that I originally signed and revealed as a signed message is the same as the message that I'm claiming was the original message. So in this way, we have a way to commit to the truth of a value, and we can commit to a value, and then there's a way to guarantee that the value that I meant originally is the value that you're seeing now. So the inverse of this is we want to, of course, the property that was implied earlier is that it should be really difficult for someone to guess what the original message is based on the hash of that message, the hash of the message with the key that it's concatenated to. So we want the hash functions that we're dealing with to work in such a way that this inference is difficult. And this is really important because, especially in the context of blockchains, there's a concept known as proof of work, which directly relies on this. That is, it should be difficult to have any systematic way in which we can guess the original value based on the hash. So there should be no real way which is significantly better than just randomly making guesses or just iterating through the space of all inputs. Given this property, this enables an important blockchain application called proof of work, which we will see later on. Another application for hashes is the salting of passwords. So while this is then directly related to the blockchain concept here, this is just useful as a way to understand why hashing is, as a way to understand how hashing can be useful. in a cryptographic context. So whenever we have passwords, what we do is we typically don't store the passwords directly. Like suppose the password is a string, we don't just store that string in the database, we take a hash of that string. Now, different users can have different passwords, which would mean that the hash of those passwords would also be consequently different if we are using a good hash function, which is collision free. However, sometimes users do choose the same password. Now, if an attacker can figure out the hash of one user's password, and if another user is also using that same password, then the other user is also at risk. So the way that we can get around this issue is we can salt the passwords. So by salting the passwords, what we do is instead of hashing the password directly, what we would do is we would, again, similar to the commitment API, we would concatenate that password with a randomly generated value called a salt. And then we would store the hash of that concatenated string as well as the salt. So for example, if you look at the example on the screen here, for user 1, you have a different salt value which is randomly generated, and for user 2, you have another salt value which is also randomly generated. Even though the passwords for the two users are the same, of course, the concatenated string is not the same because a part of the concatenated string comes from the salt value, which is randomly generated. So as a result, the hash of the passwords, even though the passwords are the same, will look different. This is an added security layer so that even if you can figure out the hash for one user, you can't figure it out for the other person. So the extra consideration here is that we also have to remember the salt value along with the hash. Now we'll take a look at the hash function used in Bitcoin just to motivate or just to give a picture of what these hash functions look like in practice. So I'll just give you a rough overview without really going into the details here. So the way that this hash function works is first, suppose we have a message. The first thing we need to do is we need to split up the message into consecutive blocks, each of which are 512 bits. Now, of course, the message might not always be a direct multiple of 512 bits, which would mean that the last block of the message would need to have some sort of padding. So we do this as procedure. So what we'll do is we'll just split up the blocks into we'll split up the message into blocks of length 512 bits and padding the last block if necessary to make it 512 bits as well. Now that we have all these blocks, as you can see, what we're going to do is we're going to do things one by one. First, we'll have a constant value, 256-bit value called an IV. What we're going to do is we're going to take this constant value, combine it with the first block, and run it through a function C, which will give us some sort of output. Now we'll take the result of that, the output of that function, and again combine it with block 2, which is also another 512-bit block, which will again go through the same function C and give us another output. In this way, we are consecutively one by one using all the blocks, and by the end of this process, we'll be using the entire message to finally generate the hash for the whole message. And this is how the Bitcoin hash function works. Lastly, we'll deal with another concept that will be important where hash functions are relevant in the context of Bitcoin or blockchains in general, which is that blockchains often operate using what we can refer to as public and private keys. Now, these public and private keys are also cryptographically related. So the public key of a user can be thought of as an address. So the way that we do this is we take the public key of the user and then we hash it to some one-way hash function and we get the address for the user. So the way that hashes work here, from a very superficial point of view, we'll go into the details later, is the private key is used to sign messages, as we discussed earlier. So later on, those signed messages, the owner of those signed messages, or to understand who signed those messages, we can use the public key to verify that. So what private keys sign and public keys verify. We'll get into the details later, but again, this is just to give you a broader understanding of how hash functions are related to blockchains and why they're so important.